properties of logarithms. And what we're going to find out is all the properties come from exponential functions. So remember what the definition of a logarithm is that b to the y is equal to x if and only if log base b of x is equal to y. Notice that base is the same thing. If I take a number and I raise it to the power, it gets an answer. If I take the log of the same base and I take that answer and I throw it into the logarithm, the thing that it outputs is the exponent. B to the y equals x, that's the exponential form. Log base b of x equals y, that is the logarithmic form. Okay, so the other thing that we know is we have two special logs. We have the common log, which looks like log m, and that means log base 10 of m. Then we have the natural log, where it looks like ln of m. Come on. ln of m, and what that means is it means log base e of m. So those are the two logarithms where we can drop the base. That's the only two where we can drop the number for our base because we use them enough that we have a shorthand. So if you see a logarithm and it looks like log without the number written there, it's secretly log base 10. If you see the ln, that can only be log base e. Those are the only two times that you are allowed to drop the number itself for the base. All right, so we want to evaluate, and we want to round to 3 decimal places. So when I see this, when I see log of 100, right, this is the same thing as log base 10 of 100. And so I'm asking, what power do I raise 10 to get 100? And it turns out you raise 10 to the 3rd power to get 100. And you can actually throw all of these in your calculator. So I just did the first one by hand because I can. So throw the other 2 in the calculator. You will not get a nice number because they are not powers of those things. Try them out, see what you get. I don't have the answers here, so we'll talk about it in class. All right. I'm sure that you're throwing them in your calculator, right? So on your paper, it has 3 graphs and 3 equations, and you have to match the graph to the equation. So the way I have it set up here is a little bit different. I have the graph, and then I have our 3 things, and I want you to take a look. So let's look at what we have. We have f of x is equal to log base b of x. So that's a logarithm. So we want to think about what were the properties of logarithms. What did we know? Did they have asymptotes? Were they vertical or were they horizontal? What was the domain like for a logarithm? What was the range like for a logarithm? The second equation we have is b to the x, where b is greater than 1. So remember, when b is greater than 1, that means that we're going to have exponential growth. And our last one is h of x. Sorry, I don't know if you can hear it, but my dog is snoring, and it's adorable. We have h of x, and h of x is equal to b to the x, where b is between 0 and 1. So it's some kind of fraction. And remember, that's the one that we call exponential decay, right? So that one's exponential decay. So I've got a logarithm, exponential growth, and exponential decay. So take a second, pause the video. Which one do you think graph A is? Which one do you think graph B is? And which one do you think graph C is? And then come back and see what we got. All right, so pause it. Okay, so here we are, graph A. And this one, if we look at it, it's coming from positive infinity, and it's, whoops, I tapped it. It's coming from positive infinity, and it's going down to and getting close to 0, but it's not crossing. So this one is definitely one of our exponential functions, And because if we read it left to right, it's getting smaller, right? The y values are getting smaller. So this is in fact exponential decay. All right, for our next one for B, this one, so our last one had a horizontal asymptote. This one looks like it has a vertical asymptote, right? And it looks like it can't go past y or x equals 0. And so this one, because it has a vertical asymptote, is in fact our logarithm. Finally, here we have our classic comes up from what looks like, as we come up from negative infinity, it looks like it's getting bigger and bigger and bigger and bigger and bigger and bigger. And as we go back down towards negative infinity, it's getting closer and closer and closer to 0. This is our exponential growth function. All right, so here's a bunch of them. I'm going to use the definitions of logarithms to evaluate each of them. So go back to this idea that b to the y equals x if and only if, that's what the double arrow means, if and only if log base b of x is equal to y. So use this idea to evaluate each of these. So you ask yourself, if I have log of 10, right, that's secretly log base 10, so what power do I take 10 to get it to the 10? So do that for all these, pause it, try it for all of them, and then we'll talk about them. Okay, we're back. I'm going to flip over to the next one. So here we are. So let's look at just the top. I have log base 10 of 10, or common log of 10. I've got log base 5 halves of 5 halves. I've got log base 24 of 24. And I have log base b of b. And if you think about it, all of those, what power do I have to raise 24 to get 24? It's just 1. What power do I raise 5 halves to get 5 halves? It's 1. What power do I raise 10 to get 10? 1. What power do I raise b to get b? It's just 1. And that one at the end, log base b of b equals 1, that is a general rule. If the thing that I'm plugging into my logarithm is the base itself, I'm just getting back 1. All right, let's look at the next one. Log base 10 of 1. Log base 5 halves of 1. Log base 24 of 1, log base b of 1. Let's ask ourselves, what power do I have to raise 10 to get 1? What power do I have to raise 5 halves to get 1? Anything to the what power equals 1? Gosh, I really hope you said 0. Anything to the 0 power is 1. So when I plug 1 into a logarithm, by golly, I better be getting 0 back, because this one I just highlighted here says, what power do I raise b to get 0? The power I raise b to, what power do I raise b to get 1? The power has to be 0. I take b to the 0 power and I get back 1. All right, now let's take a look here. I've got log base 3 of 3 to the 7. And I have log base b of b to the x. So what power do I take log base 3 of 3 to the 7? What power do I take 3 to get the number 3 to the 7? And if it sounds like a trick question, well, by golly, it is. The power is 7, right? 3 to the 7, the power I take 3 to get that is 7. It's right there. Log base b of x. What power do I raise b to get b to the x? Well, that's a trick question because x is the power, so it's got to be x. And this is, just think about it. Remember, they're inverse functions, right? If f of x is equal to b to the x, then f inverse is log base b of x. And don't we have a rule? Isn't log base b of b to the x, of b to the x. Isn't this equal to, let's see, log base b is the inverse. So isn't this the same thing as f inverse of f of x? Oh my gosh, it is. And what do we know about when we compose inverse functions? What's the thing that we're supposed to get back when they simplify? It's just x. Oh my gosh, it worked out. All right, what's our next one? This is a weird one, right? When I take 9 and I raise it to the log base 9 of 17, the thing you get back is 17. And this one, when I take b and I raise it to the power log base b of x, the thing I get back is x. And again, if you think about it, this is, if I take b and I raise it to the power log, and this is why notation is so important, log base b of x, this is the other way around, right? This is f of f inverse of x. And again, it's supposed to equal x because that's the whole point of inverses, is when you compose them, you get back your variable. Oh my gosh, what a weird, weird thing. Isn't that cool? So this is kind of the other way that you can undo logs, is if you feel really weird about flipping back and forth between exponential and logarithmic form, this is why you can do it, is these two rules. And if you want to skip the rules and you just flip back and forth between the two, that's fine, because by definition, that's true. And if you're in exponential form, you can change over to log form. If you're in log form, you can change over to exponential form. But if you're like, I feel like I'm not doing enough algebra, and you want to use these rules, log base b of b to the x is equal to x, and b to the log base b of x is equal to x, you can do that too. That's totally fine. Take the log of both sides. Raise both sides to the b. Or you take both sides and use them as exponents of b. All right. So turns out that just like powers, logarithms have properties. And there's 3 properties. And there's only 3 properties. And you can't change those properties. You can't go mixing them up. You can't match them. This is it. Nothing else. All right. First property is called the product property. The product property says that if I have log base b of m plus log base b of n, so I have 2 logs, same base, they both have something inside of their logarithm, what I can do is I can turn that in, because the base is the same, because the base of both these logarithms is the same, I can actually bring them together as a single log, and that addition turns into multiplication. That becomes log base b of m times n. And I'm going to showcase in class why this works, and I may or may not make a little video just explaining where the properties come from. I have a whole PowerPoint on just this stuff. It's kind of long. All right. Right now I'm just giving you the properties. The second property we have, and that's it. Don't change those properties any other way. The second property we have is the quotient property. Again, I have 2 logarithms. Again, they have the exact same base, but this time log base b of m has log base b of n subtracting it. All right, and addition on the outside turned into multiplication on the inside. Guess what subtraction on the outside is going to turn into? If you guessed division on the inside, you'd be correct. So again, I write it as a single log, so log base b, notice that the base hasn't changed at all, of m divided by n. And here's where this is coming from. That negative, right? N is the one that has the negative, so n is the one that goes to the denominator. Yes, if alarm bells are going off in your head because it's reminding you of powers, this all comes down to our power rules. All of these are proven via our power rules. Okay, finally, our last property, and this is the one that I think trips people up the most because it feels really, really weird, is the power property. And what this says is that if I have a number times my logarithm, my log base b of m, what I can actually do is I can take that number on the outside and I can bring it inside of the logarithm. And this actually comes out to be, and this is why I hate not having parentheses, because this should actually be p times the log, and you'll notice I do cursive L's all the time for not just natural log, but for log. So log base b, oh, my b got a little weird. Log base b of m, this is equal to log base b, and I love the parentheses here because it shows you that the p is now inside of the logarithm. So the p is now inside the logarithm. Okay, and I know that seems really weird, and we will talk about this in class, I promise. I will show you why these work and what rules they come from in your, or how they are derived from your exponential rules. And again, remember, review your exponential rules. Go back to section 7 from the beginning of the term and go check those exponential rules. All right, again, don't make up properties. That's it. We have 3 properties. Don't change them. Don't try and make up your own. Don't be like, oh, when there's addition inside the logarithm, I can do something. You can't. No, that's it. This is it. There's nothing more. Don't change anything. Don't change anything about this. This is all you can do. You can combine them together, right? So you could have p times log base b of m plus log base b of n. That'd be fine. But this is all the 3 things that you can do. All right. I'm so glad I said that. So let's try one. So go ahead and try these. Use those 3 rules. Those only 3 rules. When you're doing D, take it a step at a time. So you got those parentheses, right? I would clean up the stuff inside of the parentheses before I dealt with the subtraction. Try and clean it up and do it a little bit at a time. Go ahead and pause it. I'm gonna do A and I'm gonna do C, and then we'll talk about B and D in class. So pause it and then come back to me when you've tried them. So we've got log base 3 of x plus log base 3 of y. And the first thing that we need to do, the first thing that you should hopefully be doing, is double checking, do I have the same base? If you don't have the same base for all your logarithms, you can't do anything. This only works when those logarithms are the exact same base. And the reason why is because if they're not the exact same base, they're not the same function. And so it has to be the same function for you to be able to combine them into one thing. All right, so here we go. So what's it say? I have addition on the outside, so that turns into log base 3 of addition on the outside turns into, that's right, multiplication on the inside. All right, and that's it. It's a single log. I've dealt with everything. Let's try this one. So now we're going to do C. So 1/2 of log base 5 of x minus 4 times log base 5 of y. And again, your first thing should be to double check, are those logs the same base? And they are, so I can bring them together as one log. And from here, you kind of have some choices. I think it's easier to bring your p's in first, and to leave the positivity, negativity outside the logarithm and deal with that kind of second. So I'm going to bring this 1/2 in. So I have log base 5 of x to the 1/2 power. Minus, I'm going to bring the 4 inside, log base 5 of y to the 4th power. Okay, and I'd rather write a radical than a power, so I'm going to clean up that x to the 1/2, and I'm going to call it log base 5 of the square root of x minus log base 5 of y to the 4. Yeah, maybe I'm just showing off. Who knows? All right, now what I have to do is I need to deal with bringing them together. So I'm subtracting on the outside, which means I'm going to have division on the inside. So I'm going to bring it together as a single logarithm. So, and really, I know you're like, oh, Amy, I can do these all in one step. But honestly, don't do it in one step. I promise you something will go wrong somewhere. And there's just so many little itty bitty things that at least do it in two, if not 4 steps for most of these, okay? So don't be afraid to show your work. And it's not just for me, right? It's also for you. You want to be able to come back to your work and go, what did I do? How did I get this? And really, especially if you have a fraction or if you have kind of any addition, if you have anything more than just a single number inside of your logarithm, you need to put parentheses around there. I will 100% dock you if you don't, because it's ambiguous. Unless, if you have more than one thing inside that logarithm and you don't put parentheses around there, it is ambiguous as to what is inside and what is outside of the logarithm. So you need to be very careful and use those parentheses. So our final answer here is log base 5 of the square root of x divided by y to the 4th. And again, the y went on the bottom because the log base 5 of y to the 4th was the one that was subtraction. And the subtraction turned us into division. And if this is reminding you of negative exponents, guess what? That's where it comes from. All right. So one more time, property of logarithms. Here are those powers. Ready? The product property. Now it's the other way. Log base b. If it's n times n, if it's multiplication on the inside, guess what? It goes the other way. You can split it apart into two logarithms. Log base b of m plus log base b of n. That's fine. If you have a property that's equality, it's always a two-way street. If you have the left side and you want the right side, that's fine. If you have the right side and you want the left side, that's also okay. As long as it's an actual rule, you can always switch one side for the other side. All right, my quotient property. If I have division inside a logarithm, I can break it up into two logs, making sure I'm keeping that base being consistent for both the product property and the quotient property, and my division turns into subtraction of two separate logs. Here's my power property. If I have log base b of m raised to some power p, I can take that power p and I can bring it outside, multiplying it in front of that log base b. Again, I will talk about how the heck these actually work. What? Because really I understand the power property really feels like you're doing magic. And I will at the very least walk through that one and where it comes from. You don't have to memorize the proofs, but I'm going to show them to you just so that you feel better about them. Again, this is it. Those are the only properties. You ain't got any other ones. Don't go thinking that you can do something when there's subtraction inside of a log. Doesn't work. The subtraction has to be outside of the logarithm. Don't try and change anything. This is it. This is all you can do. These are the rules that you're allowed. Because these are the rules that just kind of self-generated. All right, here we go. We're going to expand them. So we're going to take those rules and we're going to break them apart. So you want to make sure that there's no powers left inside your logarithm. You want to make sure that that there's no multiplication inside your logarithm. You want to make sure that there's no division inside your logarithm. So I'm going to do number B. I'm going to do B. So go ahead, take a break. Don't take a break. Try it on your own. See how you do. I'm going to do B when you come back. So welcome back. I hope that you tried all of them. So we've got log base 5 of the square root of x to the 5 times y to the 6. And notice that y is not underneath the square root, just x's. So I'm going to clean up that power first so that I actually know what power x is being raised to. So this is log base 5, and this is the square root. So do you remember that this is x to the 5 halves? And if your brain just went, what? Go review section 7. Because that's where our power rules were. Go review your power rules. They're important. They're really, 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 really going to help you out. I can't emphasize it enough. Do you want me to say it again? Go review your power rules. All right, times y to the 6. And since there's not, since they don't have a similar p-value, or a similar power, I think it's easier to break it apart and then bring out the p-value. Just like when I said zipping it up, it was easier to bring the p-value in first and then bring the logarithms together. So notice how I'm doing the steps in a similar order, just backwards from each other, right? Which is exactly what we're doing. So I'm going to break this apart. I have multiplication on the inside, so I was told that turns into addition on the outside. So log base 5 of x to the 5 halves plus log base 5 of y to the 6. And now I'm going to bring my p-value out. So I'm going to take my power and it's going to pop right out. So I have 5 halves times log base 5 of x plus, I'm going to take this 6 and I'm going to pop it right out, 6 times log base 5 of y. My log got a little bit weird. My notation got a little weird right there. Started writing log like it was a subscript. There we go. All right, and that's it, right? Inside of each log, I'm going to look. I don't have anything more than just a variable. And so this, writing right on the edge, this is my final answer. Okay, so let's try another one. Let's try C. I'm going to try C. Okay, here we go. I've got common log. What base is common log? Take a second. That's right, it's log base 10. So this is secretly log base 10 of x to the 12 times the square root of y divided by z to the 6th. Okay, so we're going to have, I'm going to rewrite that y as a power. So log of x to the 12 times y to the 1/2 divided by z to the 6. And now whenever I have subtraction, because remember when you have a fraction, you've got these secret parentheses in the numerator and these secret parentheses in the denominator. I like to separate out any kind of division that I have before I separate out any kind of multiplication I have. So I'm going to do it this way. I'm going to call it log of x to the 12 times y to the 1/2 minus log of z to the 6. And yeah, I put a little line through my z because otherwise I feel like my z's kind of look like weird 2's. And I like to be able to tell the difference between a z and a 2. All right. And now this one, my common log of z to the 6, I could bring the 6 out, but first I'm going to deal with these other two. I'm going to deal with this x and this y. So I'm going to zoom out a little bit so I can actually write. So I'm going to have log of x to the 12, and then it was multiplication, so it's going to be plus log of y to the 1/2. And then this is still going to stay minus, oh, why does that keep getting weird? Minus log of z to the 6. Okay. There's just not enough room. Okay, so I'm going to do it this way. Ready? I'm going to look at each one. So this one, what happens here? Take that 12 and bring it outside. So 12 times log of x plus, what happens here? Take that 1/2, bring it outside. 1/2 log of y. And then finally, that negative still stays negative. What happens to the 6? You bring it outside. I don't know why that keeps happening. -6. I'm just going to erase the whole thing. It's driving me crazy. So we're going to say -6 log of z. And I warned you about it that people will say log instead of common log. And I'm doing it right now. So every time I'm saying log, I mean common log. I mean log base 10. So 12 times log base 10 of x plus 1/2 log base 10 of y minus 6 log base 10 of z. That's how that all separates out. So really, taking the time and taking the steps are really going to help you. These aren't hard. It's just tedious, and it's very easy to try and combine steps and then mess them up. You guys are just starting, so don't try and skip steps, okay? All right. So I think one of the greatest questions that's been on everybody's mind was, how do I plug, I don't know, log base 15 of 37 into my calculator? Because you'll notice you don't have a log base 15 button. So what we have is we have the change of base formula. And the way that it's written is it's written for just the buttons on our calculator. This is actually true for any base that you want to change to. So for any positive real numbers, b and x, where b is allowed to be a base, that is that it's not equal to 1 and it's positive. If I have log base b of x, I can actually rewrite it using either the common log or the natural log. I can actually rewrite it as any other log function. And what happens is it's common log of x divided by common log of b. So this is just in general, if a and b are greater than 0, that's positive, and a and b both don't equal 1, this is just saying that they're allowed to be bases, then what I can actually do is I can say log base b of x, and what happens is that this is actually equal to log base a of x divided by log base a of b. So this is the reason why it's both common log base 10, or natural log base e, is that this is actually just true for any logarithm base. This is just a general formula. This is a general formula to change from any log base to another log base. That did not turn out good. Let's make it nice and big. From any log base to another log base. The reason that we're using common log and natural log, the only reason that we're using those two is because those are the buttons you have on your calculator, right? You have a log button on your calculator. That log button is the common log. You have an ln, you have a natural log button on your calculator, right? So if you actually want to calculate it, you can do this change of base formula using those buttons on your calculator. Okay, so now that you know that, here's a bunch of them. Plug them in. Use the change of base formula. If you need to, If you can do it without the change of base formula, do it. If you need to use the change of base formula, do it. Make sure that you do all of these before you go check. I'm about to show you the answers. I'm just going to flip over to the next page. It's going to show you all the answers. Pause it. Make sure you plug everything in. Get an answer for everything. If it's an approximate, round it to the nearest thousandth, which is 3 decimal places after the decimal. All right, ready? Pause. Make sure you've paused it because I'm going to flip over right now. All right. So the only ones that turned out nice was log base 5 of 5 and log base 25 of 5. If you did not get these from your calculator, talk to me in class so I can help you figure out what went wrong, okay? You should write down, this is what I typed into my calculator, this is the answer I got, and then that way I can help you figure out what you need to do to fix it, okay? All right, our last thing that we have is we have another word problem. So this time we're going to calculate the magnitude of an earthquake generating 1.12 times 10 to the 15 joules. All right, so we are going to use this formula. M is equal to 2/3 of 2/3 times the common log of E divided by E naught. And we're going to be told M is magnitude. And we're going to be told E is the seismic energy released by the earthquake. And E naught is just this constant number. It's 10 to the 4.4. So let's just think about what we have. So we want to calculate the magnitude of the earthquake. So we want to calculate M. So, whoops. So we were told find M. So if we found M, then that must mean that we know the other things, right? So we know 2/3, we know log, and then we go and we read the next thing. It says E. E is the seismic energy. Oh, released by the earthquake. Weren't we told that the earthquake released 1.12 times 10 to the 15 joules? And I'm going to put a capital J for joules. Don't remember if that's the correct unit notation or not. All right, and we know E naught, it gave us an actual number for E naught. E naught is 10 to the 4.4. All right, what's it say? To find the magnitude, we're going to use that function. And exactly like I said, they gave us E, right? You always go back and you just look at the units and you say, which unit was I given? Which unit am I trying to find? Okay, so we're just going to plug it straight in. And from here, here's what I want you to do. You have that log button, that's the common log button. Throw this all into your calculator all in one go. Do it right now, see what you get back, and let's find out. When you pause it if you haven't gotten your solution yet, did you get back about 7? If you did, congratulations. So if we go back and think about it, M is the magnitude of the earthquake. So this earthquake has a magnitude of 7 on the Richter scale. And that's it. Here are some solutions to our group work. I'm just gonna pause through them so that you can double check that your work got good. This is me just reiterating those really good rules that we had about log. Just making sure that you feel comfortable.